Okay, so today I want to talk about an intro to evaluating our algorithms using asymptotic analysis. The goal of today is to have a good understanding of what people mean when they say this algorithm has a big O of n runtime or n squared or log n, etc. And understand that that language is really important to be able to understand it and to communicate in. And it's really not that difficult of a concept, so I want to demystify some of the math behind this and describe what we mean when we say big O notation. And it's going to be really important so you can then communicate with others about the runtime of algorithms, and will really help you determine what algorithm to use for the job. So first of all, what is asymptotic analysis? So when we analyze the runtime of our algorithms asymptotically, it means that we're focusing on the length of time that our algorithms take to run with respect to the input data set. So as the input data set that we're manipulating grows, how much slower does our algorithm get? And it's a really broad sense too. So we're actually trying to put the runtime length of different algorithms into these buckets. So instead of specifying or focusing on really specific aspects of the runtime, we're trying to get a very broad description of how this algorithm runs and put it into this bucket. So when we describe it as such, others will know what we mean. Just a really quick intuition on big O notation, and we'll talk about what big O means specifically later on, as well as other runtime variables like big theta. But for now, think about big O as, like for example, big O of n suggests that the runtime of my algorithm changes linearly with the input data size. So imagine that we're working with arrays. So let's say that when I input an array of size 10, my algorithm takes 5 seconds to run. So if I input an array of size 20, it might take 10 seconds to run. And it's not that simple, but that's basically the relationship. And then when I say something like big O of n squared, it suggests that the runtime of my algorithm will become slower at a rate of the input size squared. So when I double my input size, when the array that I'm passing in is twice as long, for example, and it doesn't always have to be arrays, we're just using that as an example, but when the array that I'm passing into my algorithm is twice as long, then my algorithm will take 4 times as long to run. And when the array is 4 times larger, it will take 16 times longer to run. So this has a drastic impact on how our algorithms will perform as the size of our input and the size of the data we're operating on becomes larger and larger. All right, and why is it important? So, nowadays everyone's working with big data. You want to be able to identify the right algorithms to use when you're using large data sets, or you're using small data sets, which will get bigger over time. So you don't want to use an algorithm that will be very, very slow as your client base increases in size, for example. It's also important because, like I said before, we're trying to take the very specific equation that might tell us how the algorithm runs. Instead of focusing on the very specific runtime, we're trying to put these runtimes into buckets. So we want to focus on the big picture of the runtime and the broad sense of how the runtime will change as the data set or the data size increases. And mathematically, what we'll see later is that corresponds to us dropping constant and coefficients in lower order terms and focusing only on the highest order component. All right, and so when you understand what this means, you'll see at the end of the day here that being able to run, and because we'll do some examples to show this, but being able to run an algorithm that is O of n log n is the difference between a well-performing app and a completely usable app that would be running at maybe O of n squared. So changing your algorithm up, you might get the exact same results, but using the right algorithm is the difference between Google being able to perform a search for you in 0.1 seconds versus 10 years, right? And it sounds extreme, but it really is pretty extreme. We'll take a look at some small examples in the future, and you'll see how big of a difference it makes when we use the correct algorithm. All right, cool. Also, coding interviews. It'll be important when you go there to understand asymptotic runtime. Like I said, working with big data when you're scaling your projects up. And like I've already specified, it really does develop a language which allows it to communicate with one another about how our algorithms run and be able to discuss, what's the right tool for the job. All right, cool. So let's look at some intuition here. Let's start off by imagining that we have an array with 100 names in it, and those names are in no particular order. So in the worst case scenario, if I want to go through that array and see if a name exists in that array, in the worst case scenario, what's the minimum number of names that I have to check to be sure that the name that I'm looking for is not in the array? And like all my other videos, go ahead and pause at any time to try to answer these questions before I go through the answer to challenge yourself. So in the worst case scenario, if I have an array that's unordered with names in it, the worst case is if the name I'm looking for is not in the array, which means I'll have to look at every single name before I know for sure that the name is not there. Okay, just like if I'm looking for somebody in a house, I have to look through all the rooms before I know they're not there, right? Because they could be in any room. So in the same sense, this name could be anywhere, and because it's an unordered array, I have to look through every single element in the array to make sure it's not there before I can be sure that it's not. So that's 100 checks I have to do if I have an array of 100 names. Now, think about this. Is there anything that you can do to this array to reduce the number of things you have to look at in the worst case scenario to know if the name is or is not there? And if you're stuck on that question, a short hint would be think about a phone book. I know we don't really use phone books at all, but imagine a phone book. If you're looking for somebody in the phone book, do you look through every single page and every single name on that page to find the person? Or are you able to do something different that allows you to find that name quicker? And if you are able to do something different, what inherently about the phone book allows you to do that? Okay, and so the answer is if I sorted these names and these names were in order, I would no longer have to look at every single element in this array to come to my answer. I would be able to do what I do with the phone book. So if I'm looking for someone with the last name of Bernard in the phone book, and I open up to the S's, I know I could discount all the pages to the right of the page that I'm on, because I know that this person cannot be from the S's onward in the alphabet. So then I can focus on the left half of my phone book. And if I open those up and I'm in the C's, then I can discount the left-hand side of that problem and focus only on the right-hand side of that problem and focus only on the pages on the left-hand side. And I can keep doing that over and over. And as you see, I continue to split my problem in half. Okay? And I don't want to just split in half once and then just look through the whole left-hand side. I want to keep splitting in half and use the page that I open up to in the middle to make a determination of which side, which group of pages this person must be in. So I do the same thing with this array. Right? I take the array and I want to split it in half and choose which side of the array I care about and discard the other half, and then do that over and over again. And so the question now is, all right, so I was at 100 checks before, but doing this procedure, how many checks would I have to do? And there's no one specific answer to this. It would depend how you code it, but if you can get in the ballpark, that's what I'm looking for. So I have 7, okay? So you would look at the 50th name, and then the 25th, and then the 12th, and then the 6th, and then the 3rd, and the 2nd, and finally the 1st. And if that very last name is not the name you're looking for, you know for a fact that that person is not in the array. Okay, just like in a phone book, if you open up to the S's, and then you go to the left, and you open up the C's, and go to the left, and open to the B's, and then you start half splitting the page, right? And if you finally get to 2 names where your name should be in between them, you know that the person you're looking for is not there. Okay, we do the exact same thing here. So we've determined that we can do 7 checks instead of 100. And that's really cool, but what is really powerful is how these number of checks grow as my input array size grows. So 100 to 7 is great, but what's really important is how these numbers change. So let's say what we wouldn't want to happen is if I went up to an array of 200, a size of 200, and the number of checks I would have to do, for the unsorted array would go up. Well, that'll be a question I ask you in a second. But if let's say, for the sake of argument, that they were both multiplied by 2. So if I went up from 100 checks to 200 checks when I doubled my array size from 100 to 200 for the unsorted sense, then that's fine. But if 7 also went up to 14, I haven't really made any progress by doing this way because they're both continuing to double. And if I keep doubling over and over and over again, eventually it's going to be not that big of a difference between whether I started with 7 or started with 100. And we'll see that as we move forward. So I kind of answered the question for you already that we're about to ask, but let's go ahead and just do it anyway. So if our array now has 200 people in it and it's unordered, how many checks do I need to do? And a quick pause if you want to. And the answer is 200, right? I have to look at everybody. If it's unordered, I have to look at everyone and see if that person's in the array or not. However, if I sort my array and do this phone book search method on it, how many do I have to do? Remembering that I did 7 before. Okay, and if you said 8, you're correct. And the intuition behind that is, well, I doubled the size of my array, right? And my procedure for my phone book search method was that the first thing I did was I cut my array in half and chose to use just 1/2. So after that first split, I'm back to an array with the size of 100. I know that I can solve the problem with an array of size 100 in 7 checks. That's what we determined back here, right? 7 checks for an array of size 100. So I just do one more split to get back to my original problem. So I've only done one more thing. So now I've done 8 checks for an array of size 200. So my input size has doubled, but I've only done one single more check. Now, if I'm unordered, the amount of checks I have to do has also doubled. And this is where we start seeing how powerful this runtime analysis is and how powerful the right algorithm for the job is. Some of you might be asking, well, isn't it a lot of time to actually sort them in the first place? And the answer is yes. There are times where you might want to do it, might not want to do it. That's beyond the scope. We're just trying to get intuition here. And we can talk about that a little bit more at the end. But for right now, let's just pretend like the sorting process took 0 time. Okay? Cool. So now we double again from 200 to 400. So if it's an unalphabetized list, we now have to do 400 checks because we have to look at everything to determine whether or not the person's there. And if it's unalphabetized, if it's alphabetized, we do the same procedure we did before, right? We have a size of 400. The first thing we do is split it in half and choose a half to go with. Now I have an array of size 200, and I know that an array of size 200 can be solved with 8 checks. So now I have 9 checks. Okay? And as you can see, as my array doubles, the unordered array has to be, the number of checks I have to do there has to double as well, while the alphabetized array, I only have to do one single more check every time, no matter what I'm doubling to. Okay? Notice that I did one more check when I doubled from 100 to 200, and I also did one more check when I doubled from 200 to 400, even though I was adding 200 when I went from 200 to 400, and I was only adding 100 when I went from 100 to 200. And that's the power of this. And we'll take these numbers to the extreme to kind of see why this is so powerful. So let's say that I start off with an array of 500 people, and I double my array 100 times. If I double my array 100 times, I now have this enormous number of elements in my array. Okay? And that's how many checks I have to do for my unordered array. However, my phone book search only has to do 110 checks. Yeah, and that's right, 110 checks for an array with this many elements in it, given that it's an ordered array, right? So again, discounting the fact of actually sorting the array, we're just trying to get an intuition of how powerful asymptotic analysis is, right? So we go from something that's completely impossible to something that can be done extremely quickly, just by using the right algorithm. Okay. All right, and just a little insight into how big this number is. So this number is larger than the number of bacteria cells on Earth, and we can go through in our phone book search and only do 110 checks. Okay, and we get the same answer as if we would have gone through all of them. All right, and the runtime of this phone book search is O of log n, and if you don't remember logs from math class or you feel uncomfortable with them, that's okay. We're actually going to go through them in a little bit. I'm going to hold off on that description until we get to the end, because I have a whole section on logs where we're going to talk about it in a minute. But this is a log n algorithm, this phone book search, and the linear search, the one where I went through all of them, that's an O of n algorithm. And we kind of talked about that intuition before. And we saw that for an O of n algorithm, when my data size doubles, the number of checks I would have to do, the length of time my algorithm takes also doubles. And that's what we saw here. For a log n algorithm, as my array or my input data size doubles, my runtime goes up by a constant amount, no matter what I'm doubling from and doubling to. All right, cool. So as you can see, the asymptotic nature of an algorithm, it greatly determines the runtime, especially as we start growing our data more and more. And what we're going to do, like I said before, is we're going to try to use these principles and this terminology to take our algorithm and put them in buckets, right? If we could say, if we're classifying our phone book search, which we'll learn the official name for that later, but if we're taking our phone book search and classifying it as an O of log n algorithm, and you understand what log n means, and we're comparing that to an n squared algorithm, which would be even slower than the linear search we looked at before, now, just with those two terms, we know the basics of how this algorithm is going to perform as our data set grows, and we know which one to choose. All right, so we're going to take a look at why the specifics of the algorithm are negligible in comparison to the overall asymptotic runtime. So imagine in our previous example, if we had to do a specific number of operations to set up our algorithm. Let's say I had to do 500 things, 500 lines of code, or 500 operations, I should say, to be ready to perform my phone book search. As the array, while that might have been significant when my array was of size 100, because instead of 7 checks, I do have to do 507 checks, which is more than the 100 checks that my linear search would have to do. As that array got larger and larger, the fact that I had to do 500 operations in the beginning would soon become negligible, right? Once I started doubling my array over and over and over again, and my O of n algorithm, where I searched through everything, that became huge. The fact that I was doing 500 extra operations in my phone book search would soon not really matter at all. And that's kind of the intuition of why we don't really care about constants and we don't really care about lower order terms. All right, so let's look at some code to see the runtime in real life and take a look at code that runs in O of n time and runs in O of n squared time and how those things look different. All right, so we're going to walk through 2 examples here. The first is going to be a situation where I have an array with 40,000 elements in it, and all this does is just count how many operations I do, so we're going to discount that for now. Just understand that's going to be part of the output that we see. And the problem I'm going to solve is what is the smallest number in this array of 40,000 random elements. Okay, so I have this array filled up with random numbers from 11 to 40,011, and there's 40,000 elements in this array. And I want to find the smallest number in that array. And so we're going to look at 3 working solutions, okay? And they're all going to give us the correct answer, but they're going to give it in vastly different runtimes, okay? So this first algorithm we look at is going to be an n squared algorithm. And basically what I do to solve this problem is I go through every number in this array, and then I go through every number again. And I say, for every number in this array, go through every number in the array, and if you find a number that's smaller than it, stop looking at that number and look at the next number. So let's say that my array was, let's do this. So let's say 4, 1, 6, 8, 2, 3. I want to find the smallest number, okay? And actually, let's not put 1 right there. Let's have 2 be my smallest number. So I'm going to say, okay, so for every element in the array, look through every element in the array, okay? Set a flag of smallest is true. And as you're going through every number for the one that you're comparing it against, if you find something that's smaller, you know that the number you're looking at is not the smallest number, so break out of that loop. And then if you go through every single other number and none of them are smaller than you, then you know you found the smallest number, so go ahead and return. So the way that would look, I would start off with 4. So 4 would be my variable num, okay? So and we're pretending like this array is what's passed in as this variable a right here. So here's my array that's stored in the variable a, and num is going to be every number in this array one at a time. So the first number I want to compare to everything else is 4. And now what I do is I go through the rest of my array, and I try to see if there's anything smaller than 4. And if there is, I say, okay, if I find anything smaller than 4, I know 4 is not the smallest number, so I'm going to break and take a look at 6 next and see if that's the smallest number. Okay, so I take a look at 4. 4 is not smaller than 4. 6 is not smaller than 4. 8 is not smaller than 4. 2 is smaller than 4, so now I know that 4 is not the smallest number. So I stop looking through all the other numbers compared to 4, and I move on to 6. And I say, okay, is 4 less than 6? Yes, so I break from 6. Now I look at 8. Is 4 less than 8? Yes, so I break from 8. Then I look at 2. Is 4 less than 2? No. Is 6 less than 2? No. Is 8 less than 2? No. Is 2 less than 2? No. Is 3 less than 2? No. And now I've looked through all of the elements in my array, and none of them are less than 2. So I return 2 because the variable smallest is still true. It has not been changed to false, and I've not broken out of this loop. Okay? It just ended naturally. So the bad thing about this is that you notice that for every element in the array, I'm looking at every element in the array. So in the worst case scenario, like, it's optimized a little bit because once I find something smaller, I do stop looking. And once I do find the smallest thing, I return. But these optimizations don't matter for us when we're talking about asymptotic analysis. What matters is the fact that I am looking through every single number in the array, or at least on average case, at least something proportional to the size of my array. So I'm looking through every single number in my array for every number in my array. And you can kind of see that in the code right here. I have these nested for loops. Now, nested loops aren't a 100% indicator of an n-squared algorithm, but they're usually a good hint that one might exist. And as you can see here, for every number in my input array, I'm going through every number in my input array. So we're just going to discount the fact I have small optimizations here and just pretend like these breaks and this return doesn't exist. So for every number in the array, I go through every number in the array. So I do n things n times, where n is the length of my array. I go through the whole array for everything in the array. I go through n numbers n times. Therefore, I do n times n things, and this algorithm is n squared. Okay? Even there are going to be, like in your best case scenario, I might hit that break really quick or find maybe the first element in the array is the smallest number. Right? So the first element in the array is the smallest number. I'm just going to go through that whole array once, say, oh, this was the smallest, and best case scenario, I might come out with an O of n algorithm. But in average and worst case scenarios, and we'll talk about why we evaluate for worst case in a little bit, but in average and worst case scenarios, this is going to be an n squared algorithm because I'm doing n things n times, or at least usually doing n things n times. All right, so here I'm solving the same problem in O of n. So I said, you know what? I think I can solve this problem by just going through the entire array once. I don't think I have to keep looking through the array over and over for different numbers. So what I do is I set my smallest value to be infinity, so it's guaranteed to be larger than anything that could be in this array, unless it's an array full of infinities, in which case the smallest number will be infinity. So I set my smallest number to be infinity, and then I go through every element in the array and put every element one at a time in this variable called num. Okay? And all this is doing right here is just keeping track of how many iterations I do. So don't worry about that. And what I'm doing is I'm saying, okay, so if the number that I'm looking at in my array is smaller than the smallest number that I've seen so far, update this variable smallest to keep track of the smallest number that I've seen as I traverse this array. And at the end of the day, return that value. And that's going to be the smallest thing that I've seen. So imagine a line of people lined up, and I want to get the shortest guy. So I start off with a notepad, and I say that the smallest guy that I've seen so far is infinitely tall. And then I come to the first guy who's 7 feet. Okay, well 7 feet's shorter than infinite, so I cross out infinity and I write in 7 feet. I go to the next guy, he's 5'9". So I cross off 7 and I write 5'9". Go to the next guy, he's 6'2". I don't change my notepad because he's not the shortest guy that I've seen. And then I go on like that, and at the end of the day, whatever number is down on my notepad is the shortest guy that I've looked at. And I've only looked at everybody once. So here's an example of an O of n algorithm. I'm going through this array once. Now, I could go through it twice or 3 times. I just can't go through this array a number of times that's proportional to the length of my array. So notice here, I'm going through the array a number of times that's proportional to the length of my array. So if I said like 5 times do, as long this number right here doesn't change, so as this number went from 100 to 200 to 300, my runtime would go from 500 to 1,000 to 1,500 instead of, 100. So 10,000 to, and I'm not going to be able to do that in my head, but it would grow much, much faster as n squared. So even if I did this a static number of times, as long as the number of times I'm going through my array doesn't change proportionally to the length of my array, I can call myself O of n. And we'll take a look at that more in depth later. But this is a good example of an O of n algorithm because I'm going through my array once to solve my problem. All right, so here's another n squared solution that might be a little bit tougher to tell why it's n squared. So I'm actually using a built-in Ruby method here, select. And this is kind of like a, well, what I'm going to be doing in select is select goes through the array that I call it on and returns an array made up of elements that meet the requirement that I've set out in this block right here. So basically, I'm going to get the numbers in my array one at a time. And if any of those numbers are less than some number I'm looking at, it's going to include it in the array that I get back from this .select call. All right, so the logic behind this solution is that I go through every number in my array, and then I say, okay, so the number that I'm evaluating for in my array, I know that's the smallest number if I select all numbers less than that number, and the length of that is 0. So if I go through my whole array and select all of the numbers that are less than this number, if I come back with an empty array, I know that this number was the smallest number, therefore I can return it. And while you don't necessarily see another loop here, it's really important to understand what the built-in methods of the language you're using are in terms of runtime. .select has to go through every single element of this array A in order to make its own array with the appropriate number of elements in it. So this .select call is an O of n algorithm. I'm doing n things here, and I'm doing it n times. And it turns out that this solution is actually worse than this one because this select, even after it finds a number that's less than the number I'm evaluating for, it's going to continue to go through that array and find all of them. So at least here I have a break that once I find a number that's smaller, I break out. So these are both n squared. This one's just a more optimized n squared. Okay? And this one's actually worse. And the reason I did that is to show that when you're evaluating for runtime, you have to be really careful about what the built-in methods of the language you're using do. It's really important to know what they do. So this does n things, n times, thus is an n squared algorithm. So let's run this file and see what this looks like. All right, so I'm going to say Ruby, and this is called n versus n squared. All right, cool. So my n squared check. So notice that my O of n algorithm and my O of n squared algorithm both came back with the same answer, 11. And notice that this n squared is still running. So we might have to wait a while for that to get done because n squareds can get really slow. So in order to, for my O of n algorithm, I did 40,000 checks to come up with this answer, which is the size of my array. And that makes sense. For my optimized n squared, I did 145,000. Okay? So I did about 100,000 extra checks. Now that's actually not too bad for an n squared. So I got lucky with my first n squared and got a pretty good answer. So I must have hit a lot of breaks, and then the smallest number must have been relatively close to the front. But notice that this one right here, I guess it wasn't that close to the front. I must have just been hitting a lot of breaks because this one right here is taking a really long time. It's still running. And you're going to see it still gives me the right answer. But because I did not do a good job coming up with a procedure that was fast, and I didn't pay attention to my runtime, I'm going to be waiting a lot longer to get this answer than if I were to program this in O of n. So this is still running, and I'll go ahead and let it run, and I'll pause the video so you can see how many checks are actually completed. All right, so it finally got done, and it looks like we did 1, 2, 3, 1, 2, 3, so 416 million checks instead of 40,000 to come up with the correct answer because I did a really bad job creating this algorithm. One more quick set of examples. So something that's pretty common to do is starting off with an array and creating a frequency hash. So how many times have I seen each element in the array? Give me the count. And that's really easy to also display n squared versus n. So I'm going to go through this one a little bit faster, but just to give you a little bit more repetition of identifying n squared versus n. So an n squared solution to my problem, again, I have an array, it looks like, of 10,000 elements in it with random numbers from 0 to 90, or 0 to 100, 0 to 99. And what I'm going to do is try to from this array, create a hash saying how many times I've seen each number. Okay, so my n squared solution says, okay, so start off with an empty hash, and then I'm going to go through every element in my array, and I'm going to count how many times that element exists in that array. So I start my count off with 0, and then for that element in my array, I then go through every element in the array and increment my count if the number is equal to the number I'm looking for. And then at the end of the day, I set my key value pairs for the number and then how many times it existed, and then I return my hash. And that's a working solution. However, notice our little hint that I have an n squared solution. I have 2 loops over my entire array here, this time an iterator each. But I'm going through my array in a nested fashion, and I don't even have any breaks or anything here. So for every element in my array, I'm going through every element in the array and counting how many other instances of that exist, and that's really slow. So a better way to do it would be to start off with my hash, and I can say, okay, I think I can go through this array just once and get an accurate count. So what I do is I say, okay, for every number in my array, I'm going to see if it exists. So this is, I don't know how many other languages this exists in. I don't think that many. In Ruby, I can say or equals. What this says is if the left-hand side is defined, then don't do anything. If it is not defined, set it equal to 0. So basically I'm saying if I've seen this number, if this number has already been counted in my hash, then don't do anything. If I've not seen this number yet, set the count in my hash equal to 0, and then increment it by 1. So if I had already seen it, let's say I've already seen it 3 times, this line does nothing, and then I increment that to 4 times. If I have not seen it, I set the count equal to 0, and then I turn it into a 1. And then at the end of the day, I return my hash. So I'm just counting as I go, instead of counting every number for every number here. And this is my O of n solution. And then with Ruby, you can be a little bit more fun and use each with object, set it off to an empty hash, and then just do your or equals 0, colon, and then so basically the same logic here, except in one line. And actually, if you want to be really cool, you can say hash.new, say everything that I haven't seen yet, put a 0 as the value, and then I don't even need this first line. I can just mem of L plus equals 1, because when I tried to get a value based off a key I haven't seen yet, the default value will be 0, so I can just add 1 to it no matter what. Cool, and we're not going to run this, but hopefully seeing that code shows you a little bit about more intuition about n versus n squared. Okay, so let's talk more about why we drop lower order terms. Okay, so here I have 2 graphs, and what we're depicting here is, let's say we have an algorithm that goes through, so n is going to be the size of my array. Whenever I use this variable n, I'm always talking about the size of my input data, and we're just going to pretend like our input data is always an array. So if n is the size of my array, let's pretend like the algorithm I'm trying to evaluate goes through my entire array 50 times. So I do 50 times n operations, and then I just do 1,000 other random things. Okay, so I go through my array 50 times and then do 1,000 things. And I want to show you, why that this algorithm right here is actually O of n. And I don't care about the fact that I'm multiplying it by 50, and I don't care about the fact that I'm adding 1,000 to it. So if my input size is less than 50, I look here at my n squared curve and my n curve, and I'm like, wait, but my algorithm here is slower than n squared down here. And that's true with a small data set, but if I look over to the right-hand side here, and I look at what happens when my input array size goes all the way up to 500, no matter how big I make this multiplier, as long as it's a static number and not related to n, and no matter how big I make this addition here, again, as long as it's something static and not related to n, there's going to be some point where my higher order termed equation shoots off into space and leaves my lower order term, even with its multipliers and additions here, it's going to leave it in the dust. So as you can see, the reason that this, I don't care the fact that it's multiplied by 50, I don't care that I add 1,000 to it, is because as my input size grows, n squared becomes dominant and shoots off into space. And this is going to look closer and closer to my n line. So that means that I can call, intuitively, that's why I'm okay with calling this algorithm an O of n algorithm and grouping it in the same bucket as this red line here of n, because it's definitely in a different bucket than this, right? With small data sizes, you're going to see those differences with the multiplies and the additions onto it. But with those large data sizes, your higher order term is going to shoot off into space, and these two guys, you can tell, are really supposed to be in the same bucket, and this is supposed to be in a different bucket. All right, so let's specifically talk about big O. So we already kind of went through some intuition of why we drop lower order terms and coefficients. And also, I do want to point out that the term big O is colloquially used to mean something that that's formally described as big theta. So when I've said big O in the past and when I say big O in the future, with the exception of the next few slides, what I'm really meaning and what most people mean when they say big O is big theta. And we'll see that big theta's definition is describes a type asymptotic bounds on our algorithm, while big O does not describe a type asymptotic bounds. And that will make sense in a second. But understand that colloquially, when people say big O, they usually mean big theta, which is what that's the formal definition we're about to look at. All right, cool. So, and why are we going through the math on this? Well, first of all, familiarity, so you don't freak out if you see it in a textbook or something like that. And show you that, mathematicians like to make simple concepts look complex. So don't be intimidated by equations when you see them. Take the time to look at them and see if you can understand what they're telling you, because it's really just a formal way to say something that's probably relatively intuitive. All right, so formally, I'm describing big theta here, and again, this is colloquially what people mean when they say big O, and this describes that tight asymptotic bounds, okay? And so formally, for big theta of g of n, in order for me to say that some complex function f of n is big theta of another more simple function g of n, so if I want to say that some complex algorithm that's described by f of n is really big theta of g of n, where g of n is something more simple, there must exist positive constants c1, c2, and n0 such that 0 is less than or equal to c1 times g of n, which is less than or equal to f of n, which is less than or equal to c2 times g of n for all n greater than some constant n0. Okay, and what does this mean? Basically, all this is saying is that, let's say I have some complex equation here, but the highest order term is an n, just like we were talking about before, where I had, 50n plus 1,000. If I want to be able to call my complex equation of 50n plus 1,000 just big theta of n, where n is my g of n here, right, my more simple equation, I have to be able to prove that I can take that simple equation g of n and multiply it by some constant, so that multiplication is greater than 0, and then multiply it by some other constant c2, and be able to sandwich that complex equation in between those two multiplications of my simple equation. And that doesn't have to be true at all times. It only has to be true past a certain length of size of my data. Okay? And the thing is, g of n is always going to be our highest order term for big theta. So basically, this simpler description of my f of n will be the highest order term of f of n. So in order for me to formally be able to say, hey, I can call this complex equation just big theta of its highest order term, I had to be able to prove that I can sandwich that complex equation in between the highest order term times some constant, and then the highest order term times some other constant, once my data set is beyond some undefined size that you get to choose. So let's take a look at this graphically. All right, so my complex equation here I'm saying is a 100n squared plus 4n times log n. So my g of n is my highest order term, which is n squared. In order to prove that I can say that this algorithm that's described precisely by f of n here, in order for me to be able to say that that's a big theta of n squared, which I know it is, I have to be able to show that I can sandwich f of n in between n squared times some constant and n squared times some other constant. So, and I get to choose those constants, and I get to choose the size of the data, which the sandwiching is going to be true from that point to infinity. So I arbitrarily chose my c1 value to be 1. So I'm saying I can sandwich this f of n in between 1 times n squared and 150 times n squared. And I chose 150 because it's greater than 100, and I chose 1 because it's less than 100. All right? And here's the graph. So here's 150 times n squared. Here's 1 times n squared. And here's my complex equation. And as you can see, all I have to do is be able to prove that this blue line is sandwiched in between the yellow and the red lines past some point. And I can choose any point. So I'm just going to say past 400, past an array of size 400, and it's true for 200, and probably true down here as well. It might not be true down here, but I don't care about that, right? I don't care about my really small array sizes. So I will say past an n of 0 point of 200, let's say, I know that my blue line is sandwiched in between my yellow and my red lines. Therefore, the function which is precisely described as 100n squared plus 4 times n log n is big theta of n squared. And that's the definition of big theta. And that's why we can call it. And really, it's just a bunch of fancy equations to tell us, hey, you can describe a complex equation by its highest order term. Just say big theta of its highest order term. All right? Cool. Now let's talk about big O and what big O actually means. Because big O also has a formal definition. It's just that when most people say big O, they don't mean this definition. They mean the definition of big theta. So, as you can see, let's take a step back real quick to big theta. Let's actually, I'm not quite done with big theta, so let's finish that off first. So, big theta provides what we call a tight asymptotic bounds. I am bounded above and below. I have to sandwich my blue line on both sides, right? Which is the definition of a sandwich. Now, if I tried to lie to my boss, so if I wrote this algorithm right here that was described like this, and I tried to lie to my boss and be like, oh, it's not an n squared algorithm, it's an n log n algorithm, and I tried to prove that, no matter how big the number is that I multiply by n log n with my Charlie 1 multiplier, my C1, no matter how big that is, I'm never going to be able to sandwich the blue line with the yellow and the red line from some number to infinity. I can sandwich it within some bounds, but as you can see, at some point, my f of n will overtake this yellow line because it has a more dominant term. It has that n squared term, which will always, always, always become bigger than an n log n term no matter how big this number is, right? So basically, this is just more proof that I have to choose the highest order term. I can't just lie about it, right? That's why this is the formal definition of big theta. So now let's go over to big O. And like I said, when there is a formal definition of big O, when people say big O, they usually mean big theta, but let's talk about what big O is. Okay, so big theta, we had to sandwich our f of n. All right, we had to create what they call a tight asymptotic bound for f of n. Big O only requires there to be an upper bound. Okay, it only requires you to be able to define an upper bound with g of n. So basically, now I just say, okay, so formally, big O of g of n describes, for that to describe a function f of n, there exist positive constants Charlie and n0, right, c and n0, such that 0 is less than f of n, which is less than your constant times g of n for all n greater than n0. So as you can see, the lower bound of f of n is 0. I don't have to have a lower bound that never goes up and passes f of n from the bottom. So it's technically correct to say that if I had a function 3n plus 100, that I can say that that's big O of n cubed, because you know my constant times n cubed will be the upper bound of this, and it will never overtake this upper bound. With big theta, I'm bound. I couldn't say that, I couldn't say that, because if I said down here with big theta that this is big theta of n cubed, this lower bound would pass my blue line at some point. With big O, I don't have that lower bound to worry about, so I can just choose any term that's either my highest order term or higher than my highest order term and be technically correct. So 3n plus 100 is technically big O of n cubed, even though it's big theta of n. It's also big O of n. It's also big O of n squared, etc. But that's why people usually don't use big O in this sense. Usually when they say big O of n, they mean there's a tight asymptotic bounds of your function with n. All right, cool. And so there are some other asymptotic notations that we're really not going to go over, but just so you know they exist, there's big omega and little o omega. All right. All right, so notation takeaway, big thing is, when people say big O, they usually mean big theta, and just understanding that concept of caring about the highest order term and why we care about the highest order term. All right, so I've talked a little bit before already about worst case analysis and said things like, in the best case, this might be O of n, but we care about the worst case, so we're going to call this O of n squared. So the reason I say that is because most of the time we analyze algorithms based off their worst case. Sometimes we'll do average case, but most of the time we do worst case. And for these reasons. It's easier to calculate worst case than average runtime. Okay? It takes, to calculate the average runtime of something, sometimes that could be a complex calculation. And to calculate the worst case runtime, it's usually relatively simple. So there's that, ease of calculations. A worst case analysis is a guarantee that will never take any longer. Okay? So if I went and told my boss the best case runtime for all my algorithms, and then we used it in practice, and I never achieved those runtimes, I'd probably get fired, right? So instead, I would rather give the worst case analysis and give that guarantee that I'm always going to have this runtime no matter what situation I'm in. And then the third point is that it's actually not uncommon that the worst case scenario happens frequently. Okay, a lot of the times, not always, but a lot of the times, our worst case scenario is going to be pretty close to our average case. Now, there are some algorithms where your worst case scenario, like quicksort, for example, that we're not going to cover today, but I'll briefly mention it. So there are some algorithms where your worst case scenario might actually be relatively low probability, and the average case is a good runtime. So for quicksort, for example, worst case scenario is n squared, while average case is n log n, which is a lot better, obviously. So what you can do is either implement a quick procedure to make sure you don't hit your worst case, or a lot of algorithms will actually randomize the data, because a lot of times worst case scenario will happen because the data is ordered in a certain way. So a lot of times algorithms will just shuffle the data around to make sure that it's a very low probability that you're going to hit that worst case scenario, and then perform an algorithm where the average case will most likely get run, and it's not a bad runtime. But in general, we evaluate for worst case. All right, let's talk about logarithms. So like I said before, we're going to do a quick review of logs and kind of make them look less scary if you're intimidated by them. So we're going to use log base 2 a lot here as computer scientists for a few reasons. If we're dealing with binary data, obviously log base 2 is going to be, and powers of 2 are going to be how we think about things. But here, when we talk about algorithms, we usually also talking about log base 2 because it's common that we half split our problems and divide our problems in halves rather than in thirds or in tenths or whatever. So back in math class, you might remember log log usually being log base 10. LG log is a shorthand for log base 2, and that's what we're usually going to be talking about. So let's quickly talk about the definition of logs. So all log is, so if I say I want to find log of 8, that says how many times can I divide 8 in half until I get to 1. Okay? So 8 divided by 2 is 4, divided by 2 is 2, divided by 2 is 1. So I did 3 divisions. Log base 2 of 8 is 3. Okay, and conversely, you say what power of 2 gets me to my number, right? So 2 to the third power is 8, which is also, basically just the opposite of what we just did. 2 times 2 times 2, right? And that's really all it is. So when you say log of some number, you're just saying how many times can I divide by 2? And now it makes sense with our phone book search, right? Because every time I doubled the input size of my phone book search, I did one more thing. Well, logs mathematically work the same way, right? If I'm asking the questions, how many times can I divide by 2 to get to 1? If I double the input size, I'm doing one more division of 2. So if log base 8 of 3, or log base 2 of 8 is 3, log base 2 of 16 is 4, log base 2 of 32 is 5, right? And so as I double my input size, my output increases by 1, right? Which is why we classify algorithms like our phone book search as a log of n algorithm. All right, cool. And yeah, and just to show the power of it, we kind of already described this in the phone book search, but no matter what I'm multiplying by 2, no matter what the original number is that I'm multiplying by 2, my log answer just increases by 1, right? So imagine we have a data set of size 262,144, okay? And I'm performing an algorithm that that's described by the function f of n equals n. So I'm doing n checks, right? Or the runtime is n, proportional to the size. So if my data set grows to this number, 524,288, so if I double it, with my O of n algorithm, I'm doing 1,044 more operations. If I'm doing n squared, if my f of n was n squared, I'm doing this many more operations, which is of the order of, let's say, 69 billion about. But if my function is described by log of n, I'm only doing one more operation, right? So this is why a log n algorithm like that phone book search we talked about is so fast. And with other more complex things like sorting, I usually try to take one of the n's in this n squared and turn one of them to a log n, and go from an n squared algorithm to an n log n. Because as you can see, the log n is extremely more powerful in terms of like keeping my runtime short than n or n squared. So if I can turn an n squared algorithm into an n log n, it's a huge win. All right, cool. So let's talk about some basic tips and tricks for asymptotic analysis in real life. So one of the most frequent things that lets me reduce the runtime of my algorithms is understanding data structures. So for example, hashes and sets have O of 1 lookup time. So if you are keeping a collection of things in an array and you're constantly asking that question, hey array, do you have this value inside of you? That array keeps looking through itself over and over every time you ask it that question. If you turn that array to a set or a hash and then ask the question, now you're doing an O of 1 operation instead of an O of n operation. And usually, if you're asking an array over and over if it has something, you're doing that n times. So when you turn that array into a set or a hash, you're going from an n squared algorithm to an n. So instead of doing your lookup, which is O of n, instead of doing that n things n times, you're doing one thing n times if you change your array to a hash or a set. And actually I have a whole other video on how hashes and sets work under the hood, so check that out. If you're repeatedly resizing your collection, specifically at the front, use a linked list, right? Again, that same video that talks about hashes and sets actually will describe this in full, so I'm not going to get into it. If you want to institute a priority queue, use a heap. So knowing your data structures and what data structures provide you what tasks in good runtime is really, really important for keeping the runtime of your algorithms nice and low. Being able to visually identifying asymptotic runtime is really helpful. A good indication is a loop within a loop. It's not always 100%. Just because you see a loop that's nested doesn't necessarily mean you're in n squared. However, it's a good indication that you might be, so it's good to direct your attention to that and really figure out if you're going through your entire data set, or at least a number proportional to your entire data set n times. There are other methods to formally analyze runtime, and we're actually going to talk about that later when we talk about sorting algorithms, so we're not going to get too deep into that now. And the last bullet point for tips and tricks on this slide is understanding your built-in methods in the language you're using. Like we saw in our example when we were using Ruby, we had a loop, and every iteration of that loop, we used the .select method. If I didn't know that .select method was an O of n runtime, I might think that my algorithm was O of n and use it. And we saw that took forever to run. So really know what methods you're using, especially if you didn't write them yourself. All right, cool. And another common one, this seems kind of out there, but another common thing that that comes up a lot is the fact that 1 plus 2 plus 3 plus 4, etc., all the way up to n is actually O of n squared. So this will happen a lot if you're having an array and you're adding one element to it and you're looking through one thing and then you're looking through two things and then you're looking through three things and then you're looking through four things and eventually you're looking through the whole thing. That summation is actually O of n squared. So just because you're starting off with one and only getting one larger each time, this is still going to be an issue. Okay, so let's actually look at why that is. All right, so if we look at that summation, once my computer stops thinking. All right, so if we look at this equation here, right, so we said 1 plus 2 plus 3 plus 4 all the way up to, let's put pluses here, let's say n minus 4, because we're going up to n, plus n minus 3 plus n minus 2 plus, I'm going to have too many on this side, but that's okay, n minus 1 plus n. All right, so why would this summation be n squared? Well, it's actually pretty simple to see why. So a trick to how to add all these up instead of just doing them manually is to take the first and the last and add them together. So I take n, n times, or n plus 1 is going to give me n plus 1, obviously. And then I take the second to last and the second and add those together. And n minus 1 plus 2 is n plus 1. Then I take the third and the third to last, and I get n plus 1, n minus 2 plus 3. And so I keep doing this, and I'm going to run out of numbers when I do this n over 2 times, when I get halfway in the center. So really, I'm I'm adding all of these together, and how many of them are there? N over 2. So I'm taking n plus 1 and adding it together n over 2 times. So that's n plus 1 times n over 2. So the answer to this is n squared plus 1, or sorry, plus n over 2. Okay? N squared plus n over 2. Highest order term, n squared. All right? So that's why when you sum them all together, you have an n squared number. Cool. All right, and just to finish up these tips and tricks here, for interviews, I've always heard that the best thing to do is to solve the problem first, regardless of runtime, unless you're specifically asked for runtime, and then refactor it, just so you make sure you solve the problem. And it's always important to know what asymptotic runtime you're in. So as you're writing code, you should be very conscious about what you're writing and how it changes the asymptotic runtime of your algorithm. So try to get in the habit. All right, cool. So go ahead and answer these questions on your own if you want to. But the coding challenge that we're going to do, and I'm actually going to put out another video where I don't solve this exact challenge, but I solve a binary search. Okay, so one piece of information that I do need to tell you is that the this phone book search we've been talking about, the actual name for it is binary search. And that's what we're going to program out today as our coding challenge. We're going to program out binary search ourselves. Okay? So we're going to... I'm going to have you give this a shot, and I'm going to have another video out that programs out binary search. So even if you get stuck, it's super hard, like the last slide said. I guess I kind of breezed over this, right? So make sure you understand the answers to these questions. Phone book search is called binary search, and I want you to try to program out binary search, given what we've talked about. And it's not easy, especially if you've never done it. There's a few ways to do it. In my video, I'm going to program it out recursively and iteratively, so you'll be able to see it. And so don't feel bad if you get stuck. It's not easy to do. Give it a shot, and if you get stuck, take a look at my video. I'll show you different ways how to do it. And I'm not even going to solve this exact problem. I'm just going to be programming out binary search, so you could even watch the video and then try to use that concept in order to solve this problem. So good luck.